The James Webb Space Telescope was launched with a highly specific mandate to peer past billions of light years of cosmic dust and photograph the universe exactly as it looked right after it was born. To understand what the telescope actually found, we have to look at the material that built those early structures. Dark matter makes up the vast majority of mass in the cosmos, providing the gravitational scaffolding that holds everything else together. This animation illustrates that baseline standard model of cosmology. Dark matter pools into dense, invisible structures called halos. These halos act like massive gravitational sinkholes, dragging in the surrounding hydrogen gas until the immense pressure ignites the first stars. By tracking this process over time, cosmologists built a strict mathematical timeline. The math tells us exactly how long it takes for a halo to drag in enough mass to build a large galaxy cluster. Before the James Webb Space Telescope opened its mirrors, this strict timeline for dark matter assembly was the accepted reality of modern astrophysics. Then, JWST captured light from a redshift greater than 10. That means we were looking at a period roughly 300 to 400 million years after the Big Bang. The telescope revealed galaxies that were fully mature, incredibly massive, and emitting immense amounts of ultraviolet light. This created an immediate tension. According to our standard equations, specifically a framework called the Schaeth-Torman model, it was physically impossible for dark matter halos to grow that large in only 300 million years. As you can see in the title of this published paper, the discrepancy led to viral headlines and fringe theories claiming the James Webb observations disprove the standard model, or that the universe is actually 26 billion years old. The physics community faced a stark choice: either throw out the entire Big Bang theory or find a massive flaw in the math used to calculate the growth of dark matter. To be clear, the Big Bang is safe, and the universe has not doubled in age. The real issue is that our initial mathematics relied on extreme oversimplifications. When physicists first tried to reconcile the old dark matter math with the bright JWST galaxies, they assumed the visible matter was simply working overtime. They hypothesized that early galaxies converted their gas into stars at near 100% efficiency. But a 100% conversion rate ignores stellar feedback. As you see in this simulation, massive early stars explode violently. Those shockwaves blast the surrounding star-forming gas right out of the galaxy. Because that gas gets blown away, early galaxies could not have sustained the near-perfect star formation rates required to match the old mathematical models. With visible matter ruled out as the fix, researchers knew the solution had to be hiding in the dark matter foundation itself. Researchers solved the crisis by updating the equations governing dark matter collapse, utilizing a framework known as the DP2 model. Take a look at how this diagram contrasts the two mathematical approaches. The old model assumed dark matter collapsed into smooth, perfectly symmetrical spheres. The reality of gravitational collapse is messy, chaotic, and completely asymmetrical. When the DP2 model factors in that chaos, specifically the internal rotation and the friction of particles dragging against each other, the math shows that these forces accelerate the assembly of the halo. The mathematical barrier for a halo to form is actually much lower than we calculated. This chart maps predictions for dark matter halo formation against actual data. Focusing strictly on the far right column, the solid black line represents the DP2 model. Notice how closely it tracks the plotted JWST observations for massive galaxies at early cosmic periods. Other physicists approach the problem through the particle itself, proposing axion dark matter. In this model, delayed wave oscillations create localized, massive clumps of matter that also jumpstart early structure formation. Both the DP2 and axion models deliver the exact same conclusion. Dark matter assembled massive galactic scaffolding hundreds of millions of years earlier than our original, simplified math allowed. With the existence of this early, massive dark matter scaffolding confirmed, the mystery vanishes. Early galaxies had massive gravitational wells to draw from, meaning they could shine brightly with very moderate, realistic star formation efficiencies. This updated foundation perfectly accounts for the intense ultraviolet light JWST detected. The galaxies are massive because their dark matter anchors were already massive. The telescope operated exactly as a next-generation scientific instrument should. It hit the absolute boundary of our current mathematical limits and forced the astrophysics community to refine its tools. The standard model of cosmology survived the stress test. We didn't need to invent a brand new timeline for the universe. We simply had to stop applying smooth, simplified math to the messy reality of physics. Dark matter remains the undisputed architect of the cosmos. We finally just have the proper tools to read its blueprints.